All right, jumping into our new unit here, we start with algebraic proofs, kind of as an introduction. And we're going to start this new unit in the book here in Module 3, Section 4. We're going to break it up here to start over 2 days. And so this is from Reveal Module 3, Lesson 4 on writing proofs. And these postulates are not new. They're all in your book. The page 179, this was last year's edition, and some of the pages have changed this year. So it will be in the section. It might be the wrong page number, but that should get you close. But you're looking for 3-4. Through any 2 points, there's exactly one line. We had that before. We talked about that. That's why we use 2 points when we're naming a line. Through any 3 non-collinear points, there's exactly one plane. Again, we've talked about that before. All right. And that's what we name a plane, using at least 3 letters. A line contains at least 2 points. A plane contains at least 3 non-collinear points. Those are, basically corollary to the first 2. If 2 points lie in a plane, then the entire line containing those points lies in the plane. If 2 lines intersect, then their intersection is a point. And if 2 planes intersect, their intersection is a line. And so we've had those before. Those are some basic postulates. And so the first kind of problems you're going to have are going to be either using them in some way, as always, sometimes, or never true. And so if 2 coplanar lines intersect, then their point of intersection always, sometimes, or never lies in the same plane as the 2 lines. If 2 coplanar lines, so there are 2 lines in the same plane, and they cross, then that point, will it always, or sometimes, or never be in the same plane? And hopefully, I've explained that. Hopefully you've thought that and pictured that in your mind as we talked about it. If 2 planes cross in a plane, then the point where they cross will always be in the same plane. Right? 4 points are non-collinear. Can you think of an example where 4 points are not all in the same line? 1, 2, 3, and then 4. Yeah. Can you also think of an example where 4 points are collinear? 1, 2, 3, 4. They're all like in the same line. And so this one is only sometimes. You can think of an example when they are not collinear, but you can also think of an example when they are collinear. Okay. These properties are old properties, really. They can go way back. You've learned them at some point in like pre-algebra. We're just going to convert them and talk about them here in our classroom, in our geometries. We're using proofs. And reflexive property, A equals A, something is always equal to itself. Right off the bat here, reflexive property is not going to become super useful, but eventually it becomes the one you will use the most. Symmetric property, because I don't care how you write the answer, 5 equals X is the same to me as X equals 5. You don't need to use symmetric property a bunch in here. There will be some times where the book kind of forces it. Transitive property, now, and early on, transitive property is something we'll use a lot. All right, it's also known as the law of syllogism. All right, but we'll just call it transitive property. But there's quite a few times where it's the case. And so A equals B and B equals C, then A equals C. Think about like this. If Mr. Connell is as tall as Mr. Davis, and Mr. Davis is as tall as Mr. Weimer, it's probably not fair. Mr. Weimer's too tall. So we'll say Mr. Mitchell, all right? Then Mr. Connell is as tall as Mr. Mitchell. Right? You compare me to Davis, you compare Davis to Mitchell, and so therefore you can compare me to, right? We do this all the time in sports where we try to force the transitive property. The Huskies beat the Bulldogs beat the Crusaders, so the Huskies are better than the Crusaders. And so, that line of thinking is easy, but also a transitive property is pretty difficult to see inside of a math problem or a proof. All right. We had this before. A proof is a logical argument. These are the kind of proofs the book's going to go over. All right, we're going to focus today on 2-column proofs because that is the one we'll use most frequently. All right. And so they're always will have a given. always be a given and always something you're trying to prove. And so it says Q is the midpoint of PR. What does that mean? Well, remember, midpoint means bisects. All right. So the given is always trying to help me. I'm never going to waste your time with the given. So the given means bisects. Bisects means what? It splits it into two equal parts. And so they want you to say that those two parts are equal. So PQ is equal to QR because that's what midpoint means. That's definition of midpoint. So they told you it was the midpoint. You had to think through what that meant and then put what that meant. Now, if they're equal, does that mean they're congruent? Yes, absolutely. That's what congruent means. So because they're equal, I can say that down here, that PQ is equal to QR, or that segment PQ is congruent to segment QR because they're equal. So if they're equal, they're congruent because that's the definition of congruent. And so you got to get used to just, think it through on one. I like to think it through on one side and then kind of fill these in. Right? You can do it at each step as you go. And we're going to, give you ones like this today too, where they kind of broke it down for you. And so you just got to think through a couple parts of it. Now on our homework though, I would like to see you write out the whole proof, all 6 steps. So, just get used to it. I know that I'm not saying it's fun. All right, but it is good to get used to that you got to write out all the steps of the proof. And so here that's the given, that they're congruent. What does congruent mean? It means they're equal. So I can say AB equals CD. What changed from this step to this step? Well, they had AB, now they have AB plus BC. They had CD, now they have BC plus CD. So they added BC to both sides. If I add the same thing to both sides, that is called the addition property. Just like it was when we were doing algebraic proofs. Right? Now, this maybe seems strange here, all right? But this is AB plus BC equals AC. Is that true? Does AB plus BC equal AC? Yes. So 2 parts make a whole, right? So anytime they're talking about 2 segments making a bigger segment, we call that, if you remember from earlier unit, we call that segment addition. And technically it was a segment addition postulate. I'm going to write that in here too. So segment addition postulate. And then they use substitution because they just say, okay, well, I know I have AB plus BC already. And so if that equals AC, I can plug AC into its place. Same thing, they plug BD to its place. And so they use substitution. And if those 2 are equal, then they're congruent because that's what congruent means, definition of congruence. And so again, they're trying to help you think through it by giving you some of it around which to do. And so you can use the steps above and below to kind of help you think through it. And so this is one of the problems in your homework. And so let's go ahead and start it together. And so JK is congruent to LM, step 1, because that's the given. And I should probably give myself some more. Actually, probably should write a little smaller and give myself some more space. So JK, segment JK is congruent to segment LM because that was what it was given. Right? Technically, I should probably write JK as this and LM as this as given. I'm going to leave that out right here, but we probably should write all 3 as the given because it really is giving you that as well in this picture. Right? But then I'm going to say, because this is JK right here, I'm going to plug it in for JK. Because this is LM right here, I'm going to plug it up in for LM. Congruent means they're equal. I guess I should say that first. JK is equal to LM. Definition congruent. Congruent means they're equal. And so now I can plug in 4w plus 1 equals 6w minus 6. And that was substitution. Plug it in. Just like when I come off the bench in a sporting event, I substitute in. When I plug something in math, it's substitution. Right? There's lots of, now it's an algebra problem. There's lots of ways you can do it. I'm going to minus the 4w over. And so I'm going to get 1 equals 2w minus 6. Right? I minused 4w to both sides, so I did subtraction. If you show your work, you got to write subtraction and then substitution. Or, I'm sorry, simplify. I add 7 over to both sides. I'm kind of running low on space, but I would get 7. I add 6 to both sides to get 7 equals 2w. All right. I added 6 to both sides. That's addition. And then I divided by 2, and I got 3.5 equals w, which is the same to me as w equals 3.5. I got that by division. Those are all properties. So it's division property, technically. You can write division. And that's what I was trying to prove. So I know I'm done. I'm done. And again, you show work, there's going to be a lot more steps to it. Right? So you got to figure out the steps thing for yourself. But that is thinking through a 2-column proof there. 5 through 10 are those always, sometimes, never problems. 12, 14, and 16 are proofs. You may write 2-column proofs. I think one of them is set up as a flow chart. Feel free to switch it to a 2-column proof. All right, please route the entire proof and get through them. Use some struggle. I know we'll go over it in class. All right. Good luck.